Hello viewers, I am Kausalya. Today we are going to discuss about the topic series resonance in AC circuits. So what do you mean by series resonance? Whenever you have resistor, inductor and capacitor connected in series and when resonance occurs in series circuit, then that is known as series resonance. So what do you mean by resonance? At resonance, the circuit will be purely resistive. That is, the reactive part of the complex impedance must be zero. That is, XL and XC cancels each other and the circuit will act as a purely resistive one. Right. So here in other words, you see, instead of writing XL equal to XC, here we are writing it as XL minus XC is equal to 0. Right. That is, XL is equal to XC under resonance. When you move this XC to the left hand side, that becomes XL minus XC equal to 0. Right. So here you see, that is the thing that again happens. You see, XL is equal to XC. This is what happens under resonance condition. So XL is L omega and XC is 1 by omega C. So when you rearrange, when you make omega together, finally omega square is equal to 1 by LC or omega is equal to 1 by square root of LC. Right. Let this be your equation number 1. Now, what happened to the power factor at resonance? At resonance, the value of power factor is 1 because the entire impedance value is simply equal to R here. Right. Therefore, the value of I is given as E by Z. In other words, even we can write E by R because Z is equal to R here. Right. Now, the next thing is, if L and C are kept constant and frequency is varied, right, because this is your formula for omega equal to 1 by root of LC. Okay, this gives the formula for resonant frequency because omega is nothing but 2 pi f. Right. So here in this case, if L and C are kept constant and the frequency is varied, right, then that frequency is known as angular resonance frequency and it is denoted as omega naught. Okay, which is again equal to 1 by root of LC. So here omega naught is nothing but angular resonance frequency. Right. So as we all know, omega naught is nothing but 2 pi f naught. So f naught is given by omega naught by 2 pi and again omega naught is nothing but 1 by root of LC. Therefore finally f naught is given as 1 by 2 pi into square root of LC. Right. So again now we are considering a series RLC circuit and as we all know, ER represents the voltage across R, L represents the voltage across L and C represents the voltage across EC represents the voltage across C. Right. So I is the current that flows through the circuit. So here you see the value of impedance is given as R plus J into XL minus XC. Right. So when you square on both sides, that gives Z square is equal to R square plus XL minus XC the whole square. And Z is nothing but square root of R square plus XL minus XC the whole square. Right. So again, at resonance, the value of power factor is equal to 1. So cos pi is equal to 1. What do you mean by cos pi? Cos pi is nothing but R by Z. So finally, at resonance, the value of R is equal to your impedance. Right. And again, under resonance, what happens? XL is equal to XC. So when you substitute the values here, that is omega R L is equal to 1 by omega R C. And finally, again, the value of resonant frequency is 1 by root of LC. So here omega R is 1 by root of LC and omega R is nothing but 2 pi FR. Right, and again FR is 1 by 2 pi square root of LC. So here there are some points to be noted. The first thing is, you see at XL equal to XC, when both the things are equal, the impedance value becomes minimum because it is equal to R here. Right. So this is your first thing. And the next thing is, as the impedance is minimum, what happens to the current? Okay, the current is maximum. Therefore, again the current is given by IR, that is resonant current, is equal to E by ZR. Right, this ZR is nothing but, that is impedance at resonance is equal to our resistance R. So IR is nothing but E by R. Right, and again the third thing is power. Okay, so what is the formula for power? It is I square R. So here under resonance condition, therefore IR square R. IR is nothing but E by R. Right, so again when you take square inside, okay, this R square and R cancel each other, and finally we are getting the value as E square by R. So the next thing to be noted is the voltage across L is given by I into XL, right, and voltage across capacitor is I into XC, right. Then in an RLC circuit at resonance, okay, both the voltage and current are in phase because the circuit acts as a pure resistive one. So in a resistive circuit, what happens? The voltage as well as the current are said to be in phase, right? There is no lag or lead. So while representing it in polar form, E is given as magnitude of E with angle 0 and I is given as magnitude of I with an angle 0. Right. Now the next thing is how to draw phasor diagram. So here we are going to consider three different conditions. Right. So here the first thing is we are considering XL is less than XC. Right, and again the frequency is less than your resonant frequency. So when XL is less than XC, what happens? Automatically EC is greater than EL. Right, can you get? Yes. So here, since the value of impedance is less, that is inductive reactance is less, right, so here the voltage lies in this quadrant, right. So as we all know, this is your voltage drop across resistor and this is the voltage drop across inductor and this is the voltage drop across the capacitor here. So therefore here we are having our E for this condition, right. And the next thing is for a circuit under resonance. So what happens here? The frequency is equal to resonant frequency, XL is equal to XC, therefore EL is equal to EC. Okay, they are equal and they are exactly opposite to each other. Right. So this is the phasor diagram of a circuit under resonance condition. And here the next thing is we are considering this phasor diagram. You see here the inductive reactance is greater than the capacitive reactance. So what happens? You see our total net voltage E falls in this quadrant, right. So here in the previous case, XL is less than XC. What does it mean? That is the capacitive reactance is greater. So here we are having our total voltage E. But in this case, you see the value of XL is greater than XC, therefore E lies in this quadrant, right. So here comes the end of this video. This is a basic introduction about a series RLC circuit. If you have any doubt, let me know in the comment section. Thank you.